Good afternoon everyone. I welcome you to the fifth session of NPTEL tutorial combinatorics. So today first we'll discuss some of your doubts and then we could discuss the problems from week 5. So Anuj, you wanted to discuss assignment 2 question 4 and 5, right?
Right.
Okay, yeah. So is my screen visible? Yeah.
Yeah, I can see.
Yeah. Okay. So assignment 2 question 4. So question 4 says, wait. Okay. So you have to find number of sequences of 10 ones and 10 minus ones such that sigma, so you have to find the sequence till A1 till A20, and the condition is that each of the partial sum A1 till AN should be greater than 0, right?
I think greater than equals to 0 it is. Non-negative.
It's non-negative. Wait. So we are yeah.
So I'll just tell you one approach there. Let's say a partial set.
A1 till A1 plus A2. Yeah, what's your approach?
See, the number of positive ones will be greater than or equal to the number of negative ones. Yes. And we can place it at any order. I think the order is also important over there. Means let's say I write plus 1 followed by 1 minus. And those can be arranged via 3 factorial divided by 2 factorial base. And similarly, if we have 5, if I choose.
Okay, so you are saying so first of all, order does matter. You said that order won't matter, right?
Order does matter.
Order does matter, yes.
Yeah, but see, the arrangement of 3 plus 1s and let's say 2 minus 1 will be 5 factorial divided by 3 factorial into 2 factorial.
Okay, you are saying, so first you are arranging 3 minus 1, 3 plus 1 and 2 minus 1.
Minus 1.
Yes, so like you are talking about this A1 till A5, suppose. And you are saying that arrangement for this will be 5 factorial
by 2 factorial into 3 factorial.
And this is because, okay.
So we did one calculation mistake. So I just want to know whether this.
Yeah, but why? So why are you getting this term? Like, can you tell me?
See, the partial sum, when initially if I taking only one number A1 over there, so it has to be plus 1.
Okay.
When I'm finding the 2 ones, 1 plus 1 and 1 minus 1.
Yes.
And then we can have both the positive ones. So we can have those arrangement.
Yeah.
Plus,
but see, this term. Okay.
On the same approach, I'll carry on till I don't get the 20.
Okay, but like this. Okay, so please repeat your argument.
See, what I'm saying that initially I start with when I'm taking the partial sum. Initially only one term is there, so I'll be taking 1 there.
Yes. For 1 we know it should be 1. For 1, yeah.
And when I'm taking 2 terms.
Now for A2 we have 2 options.
2 possibilities. Yes. Plus 1, minus 1 and 2 plus 1.
And minus 1, yes.
So this can be done via 2 ways only. Okay. 1 followed by minus 1 or minus 1 followed by plus 1.
Yeah, 1. So you have for A2 you have 2 options. For A3 now.
A3 will be the number of options we'll have. We can have all the 3 ones plus 1s. And then
no, what is your so see, we are constructing a sequence, so it can take either 1 or -1. So 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 this term that you are giving me, 5 factorial by 3 factorial 2 factorial, this is basically arranging one, so you are arranging 3 plus 1 and 3 plus 1 and 2 minus 1. So
correct.
This is counting all such possibilities. So this number is also counting this possibility, but we are not supposed to count this possibility, right?
Which possibility? 1 minus 1 followed by 1 1.
Yeah, this one, -1 -1 1 1 1, because like when you're calculating
what exactly your A5 is? It's a summation of 3 1s and 2 minus 1, where the order may be any.
No.
So I misunderstood, I think, the partial sum.
Yeah. Oh, okay. I think, yeah, you have some confusion in the question. Question is basically this. So now you think the question is, you have to construct a sequence till A1 A20. So each of these AI can be 1 or -1. Okay. And now you have to your sequence should satisfy this property, that each of this partial sum A1 to AN, for any n, this should be non-negative. So this will happen. So this is the question, and this will happen only if you want that this term is non-negative. So number of positive ones at each stage, positive ones at each stage should be greater than equal to number of minus ones, right? Then only this partial sum will be positive, non-negative.
Carlton number can be the final answer, I think.
What
Carlton number is there?
Yeah, exactly.
I misunderstood. The question was not clear.
Yeah, exactly.
What I did, means so A5 I found separately, but even though my answer was smaller than the actual answer.
Okay. So here, hence, since you said that it will be Carter number, so basically it will be, so this is like counting north, so it will be 1 by 11. 1 by 11, 20, choose 10, right?
Yeah, correct.
Okay, this is the answer.
Yeah, clear. Actually, partial sum misunderstood. How to?
Yeah.
A5 I thought means all the possibilities where the summation will be positive.
Oh, okay.
Considering the 5 entities, means I can have all the 5 ones. I can have 4 positive 1 and 1 negative 1. That can be arranged.
I see. Yeah. Okay. So I see. So you took A5 as to be basically fine. Constructing sequences of 1 and minus. What are the possible constructing sequences such that this property hold?
Yeah, exactly.
Okay. Yeah. So this is the answer.
Yeah, now it's clear.
Okay. And now the next question that you had problem with was question 5, which is basically, I think, permutations of 18. Permutations of 18 elements, 1 till 18. So permutations you have to count A1 to A2, A18, such that AK minus K is divisible by 3, right?
Yes.
This is the question. So did you try this? Do you have any?
Yeah, I tried actually. I made 3 partitions there, where I selected the numbers in 3 different forms I kept. 3n, 3n plus 1 and 3n plus 2.
Yes, 3n plus 1
and 3n plus 2.
Yeah.
So 3, 6, 6, 6, there will be each of the possibilities.
Yeah, so this will have multiples of 3, which is 3, 6 till 18.
Any 2 numbers if I select, the possibility of selecting the same number is also there.
Yeah.
So 6 into 6 ways we can select, and 3 such groups are there.
So so you are 3 groups are there. These groups you are talking, right? 3 till 18, 1 to 4, 15, and 3n plus 2 is basically 2, 5, and 17.
Yeah.
So so first step was partitioning this into 3 cells. And why did you partition it like that?
Because any two number, if I select that, it has to be divisible by 3.
Yes.
Because the remainders remain same there.
Yeah. So we need AK minus K is divisible by 3. Therefore, AK and K should leave same remainder.
Right.
That's why we are selecting. Very good. Should leave same remainder when divided by 6. And now we have to find the permutation. So now what you did next?
See, from first I can select 3 ways any other group.
First you select
3. I have divided all these 18 numbers in 3 different groups.
Yes.
Group A, Group B, Group C.
Yes, this is A.
So I can select any other group via 3 ways.
Any other group?
By 3 ways.
Okay.
And there are 6 possibilities in each other group. So for 2 different numbers, we have 36 possibilities to select.
Okay. I didn't understand the 3 groups. Like 3 ways to select what?
There are 3 different groups are there.
Yeah, there are 3 different
One
groups.
group belongs to all the numbers in the form of 3n.
Yes, which is
one
this.
One group belonging all the numbers 3n plus 1, and one group belonging all the numbers in the form of 3n plus 2.
Yes, yes. Yeah.
Let's say I decide that 3n plus 2 group I have taken.
You are deciding that 3n plus 2?
And group I have taken. And from there, I can pick one number via 6 ways.
Okay.
And another number I can pick via 6 ways.
Okay.
So that is 36 into 3 has to be the answer.
36 into 3.
Yeah.
So see, like, why are you selecting, please repeat your argument again.
See, any of the group I can select. There are 3 groups are there. Because if
so
why are you
first of all, why are you selecting a group?
Because I have to select 2 numbers from each of the group in order to make that difference divisible by 3.
Yeah. Oh, okay. Oh, but the okay, so I see. So you are selecting one. Okay, okay. So you are saying first you are selecting 3, and then you have. Oh, I think here also you misunderstood the question. So what you are doing is you are choosing two integers such that this property holds. So first you are choosing a group which you can do in 3 ways, and then you are choosing 2 integers from that group which you can do in 6
into 6.
Yeah. Oh, but the question was not that. Question was you have to find the permutation of the set A118. That means you have to find a bijective function from 1 to permutation is what? A bijective function from permutation of this set means you need to find a bijective function from 1 to 18, and AI basically refers to the image of I. So you want to choose, count all bijective functions which satisfy this property. Bijective functions such that fi minus I is divisible by 3. This was the question. You just don't need to select. You don't have to just select 2 integers A, I, and K such that. Do you understand the question?
Okay. Yeah, means we have to form a set like this. So can you explain this one?
Basically, find all the bijective functions. You have to. What is a permutation? Permutation is a bijective function from 1 to 18, right? So basically, you have to assign a distinct number to each number. So
how will you solve?
Yeah. So see, your first step was correct. So now you want that. So your fi minus I should be divisible by 3. So this means that this implies that fi and I should belong to the same group, right? belong to the same group. So basically, if you have to, and should belongs to the same group. So basically, if you have your so any image of so basically your function is going from A union B union C, right? And you have to construct a function in bijective function from A union B union C such that A goes to A, B goes to B, and C goes to C. Is this clear? Because is this fine?
Yeah.
Now, so now if you have, since A goes to A, B goes to B, and C goes to C. So now constructing such permutations is same as constructing, giving a permutation of A union B union C. In this case is same as giving a permutation of A, B and C separately, because all the elements of A are going to A, all elements of B are going to B, and all elements of C are going to C, and they are not allowed to go into other set. Therefore, if you want to give a permutation of this, so basically any element in A has to go to A, any element in B has to go to B, any element in C has to go to C. So you construct a permutation of this. You give a permutation of A, you give a permutation of B, and you give a permutation of C. So how many? Now your A is basically this, multiples of 3, which is 3, 6, 9, 12, 15, 18. So what are the permutations of this set A? Order A is 6. What are the number of permutations of A?
6 factorial.
6 factorial. Number of permutations of A is 6 factorial, and similarly number of permutations of B is 6 factorial. So your answer is 6 factorial into 6 factorial into 6 factorial. Permutations of A, permutations of B, and permutations of C. Is this fine?
Yeah, it's understood. Actually, I specifically for the two numbers.
Yeah.
It's my interpretation was selecting a 2 number so that those 2 numbers are divisible by 3.
Yes. But yeah, so yeah.
But the entire permutation will be 6 factorial into 6. Correct. I understood. Yeah. Thank you so much.
Yeah. Okay. So there was this another question in assignment 2. Did you try that? So you had to compute. Okay. So I'll see. You had to there was one more question in assignment 2. You have from assignment 2.
Yeah, this I could solve.
This sigma I going from 1 to 80, I 80 minus I in 2 ways, right?
Yeah.
So how did you compute? There are many ways
80
to
into
do this.
sigma n we can write minus sigma n square.
Yeah. We can. What you're saying?
Means if I open the bracket 80i it will become minus I square it will become, and then sigma 80 into sigma n up to 1 to 80 and minus sigma n square.
Yeah, this one, right?
Yeah.
And then you know the formulas for both of these, and then you do it, right? But they said that compute it in 2. Like this is it doesn't make sense because it's like a MCQ, like a one-word question. But it says that you compute it in 2 ways. So this is like a computation. Did you try to compute this combinatorically?
Combinatorically, we can just. I need to think it.
Yeah. Okay. So there is a combinatorial.
So leave it. I'll think it again. Then I'll ask in the next class.
You can think this again. But now in this week we did this. So there is a combinatorial way. Like you can use you can connect this to composition in some manner. This number. Okay. So there is relate this to composition when you're. And there is another way which we did in this week, which was generating functions.
Okay.
So we can discuss so are you like, did you revise these generating functions and
No,
products?
not yet. I didn't get time. I
Oh,
have to revise it.
okay. So okay, but we can attempt this question. I'll use you or tell all the ways that we are using it. So I won't assume anything.
Okay.
Okay. So if you want to do this combinatorically using generating functions. So this is our question. Suppose, right? So now generating function bn suppose is your generating functions. So it is basically uh, it's like it is a we can we have this recursion relation, and we call this as a generating functions for bn. So basically your b1 b2 they are computing some combinatoric things, and b1 refers to like when you are computing it with respect to 1. So this is your generating function, and similar this is what is generating function. And if you have two generating functions like this where bn where small bn is computing some numbers and cn is computing some numbers, then you can talk about product of generating functions. Then you can talk about product of generating functions. So your bn cn will be what, like if you want to write it in power series, it will be just sigma so what is with a sum, like if you are multiplying these, so what should be the if you are multiplying these two power series, so what should be the coefficient of xn, x raised to the power n, when you are multiplying these two power series. So this power series is b0 plus b1x and so on. This is c0 plus c1x plus c2x square and so on. So now you have this power series. So what is the coefficient of xn? Can you say?
It's C and xn.
Yeah, you are multiplying these two terms, these two power series, and like these two power series. Now we are trying to compute the coefficient of xn. So first of all, what will so suppose this power series is, I'm saying dn. So what is d naught? D naught. So basically if you are multiplying these two power series, what is the scalar term? It is just b naught c naught, right?
Okay.
And what is d1? That is coefficient of x. What if you are multiplying this basically you are multiplying b0 plus b1x till so on, c0 till c1x. What will be d1? That is coefficient of x.
Yeah.
It won't it be like, so when you are multiplying
It
these two
will be
terms,
C1 into B0 and C0 into B2.
yeah, b0 c1 plus b1 c0.
Yeah.
So and now you can generalize it. It is so if you want to find the coefficient of xn, it is basically bi c n minus I x raised to a power n, where I, yeah, sorry, bn cn, which is sigma n greater than equal to 0. And what is the coefficient of xn? This is basically bi c n minus I, right? I going from 0 to n. Is this fine?
Yeah.
Now okay, so now suppose you have this power series where b1 is equal to bn is equal to 1 for all n. So what is the generating bn is equal to 1 for all n. So what is the generating function for this? This is just 1 plus x, because bn is equal to 1 for all n. This is just 1 plus x square plus x cube and so on. And we have a closed form expression for this. This is basically 1 upon 1, your geometric series, right?
Yeah.
Like when mod x is less than 1. So for bn equal to 1, like if we consider this kind of function, then we see our generating function is coming out to be this. Now these generating functions behave well with differentiation also. behave well with differentiation. So basically what I'm going to say, if my 1 upon 1 minus x is 1 plus x square plus x cube, and if my another generating function, so my function is dn is equal to n minus 1. So I am, if dn is equal to n minus 1, I am basically considering for n greater than equal to 1, I am considering power series of this type. 1 plus 2x, oh sorry, n plus 1, I meant n plus 1, 1 plus 2x plus 3x square and so on. If this is the function, this, then you see, like if you, this is basically, if you want to, so now this is my, suppose this is my, I want to find generating function for this sequence where dn is equal to n plus 1. So now this behaves well, our power series behave well with differentiation. So we can see if we can differentiate both these sides, LHS and RHS, and we'll see, we'll get that this is 1 upon 1 minus x whole square when we'll differentiate it with respect to x, and this will be 1 plus 2x plus 3x square and so on. So we see that generating function for dn equal to n plus 1 is 1 upon 1 minus x whole square. Okay. Now why we are doing this? We want to find closed form expression of this. We want to find closed form expression of this using generating functions, which is saying sigma I going from 0 to n I n minus I. So we see there is a product involved. So what I am trying to do is, I am trying to find using generating functions a suitable power series whose nth coefficient will be this. So we are looking for generating function Hn such that Hn is our required number. So since this is a, now, so see, you see that this, so if this, our Hn is this, we are kind of backtracking, and I'm saying, and there's a hint that we want to use products. So this will be our Ci and this will be our Di, Dn minus I. We are expressing this as we are trying to find this power series which is coming, whose nth coefficient is this, and it is coming out to be a product of power series where Ci is I and Dn minus I is equal to n minus I. So this is your power series. If Ci is equal to I, your power series is x plus, because so if Ci is equal to I, so Ci is the coefficient of x. So your big power series Cx is just for 0, scalar term is 0, then you have x, then you have second term coefficient of x square is 2, this is 2x square, then you have this coefficient of x cube is 3x cube, and this again you can see it is basically x multiplied by 1 plus 2x plus 3x square and so on. And so this is basically x into power series of 1 upon 1 minus x, 1 upon 1 minus x whole square. Is this fine? Why this power series x plus 2x square plus 3x square is coming out to be this? Is this okay?
Yeah, it's clear.
Yeah. So see, and dn minus I is also this. So basically these two are same power series. Your dx is also this, x into 1 upon 1 minus x square, right? So now when you when you multiply this cx into dx, if you consider this as your power this as your another generating function, the product of cx dx, won't the nth coefficient will be this, right?
Yes.
Yes, because cx is basically nxn, cx is basically nxn, n greater than equal to 0, and this is also dx is also n greater than equal to 0, nxn. So now if you want to find, now if you want to find, now we want to, now if we want to give a closed form expression of this, so this we see that when we multiply this, we get sigma n greater than equal to 0, sigma I going from 0 to n, I n minus I xn. So now we want to find a closed form expression of this. So we know the LHS side also. This is basically 1 upon 1 minus x whole square into 1 upon 1 minus x whole square, and there was x also. So your cx was x upon 1 minus x whole square. So is this fine? We get that x upon 1 minus x whole. So we are getting that x square upon 1 minus x to the power whole, this is equal to this. Is this fine?
Yes, clear.
So now what we want to do, we want to find the, now we have this and now we have this. So this term is basically coming out, now if we want to find the closed form expression of this, basically we have to find what, finding a closed form expression of this is same as finding the coefficient of x raised to the power n in LHS. Because if LHS is equal to RHS, each of the coefficients should be equal, right? So if you want to find a coefficient of closed form expression of this, you want to find the coefficient of x raised to the power n here. Is it fine till here?
Yeah, it's clear.
Now, okay. Now, do you have any idea like how can we find a closed form expression of this? X square. This is basically x square into 1 minus x minus 2.
Yeah, this 1 minus x raised to the power minus 2 can be expanded with 1 plus 2c1x plus 3c2x square, like this.
Yeah. 1 minus x raised to the power minus 2. So this is basically generalized binomial coefficient, right? You are talking about that only, right?
Yes.
So, and this is basically sigma n minus 2 choose n minus x raised to the power n, right?
Yeah. So that will be 2c1x and then 3c2x square, and like this it will go.
Oh, 2c1 what?
2c1x.
Yeah, but this is minus 2. So like when you have so choose this c1 2c1x, this thing. So we wrote this n choose x to be ncx only when this n was a natural number, right? So what does generalized binomial coefficient does? It takes so what is your n choose x, n choose k? If you open it up, it is basically n factorial by k factorial by n minus k factorial. Now when your n is a natural, when your n is not a natural number, factorial doesn't make sense. But what does make sense, you can this term can be written as n into n minus 1 into n minus k plus 1 into n minus k factorial by k factorial and n minus k factorial. So these two terms get cancelled. So you basically so you can write your n choose k to be n minus 1 till n minus k plus 1 by k factorial. So now what this is when your n and k are both so when your n and k were both natural numbers, factorial was making sense. But now we are doing this generalized binomial coefficient. So it is basically generalizing it for when your n is a real number but k remain to be a natural number. If n is a real number and k is a natural number, this RHS still makes sense, right? Because k factorial makes sense when you have it is a natural number. So this RHS makes sense. So this you give your definition that if your a is some real number and k is a natural number, then generalized binomial coefficient is, this is the definition. We generalize the definition of binomial coefficient from natural number to all real numbers in this manner: a minus 1, a minus k plus 1 by k factorial. Is this fine?
Yes.
This is definition. Okay. So now to find the close, now what we were required to find closed form expression of that term, sigma k n minus k going from 0 to n. So first we saw that this is coefficient of xn in x square divided by 1 minus x whole square. Now if we want to find the coefficient of xn in this, we use our formula of generalized binomial coefficient, which is x square 1 minus x minus 2 is basically your n x square outside, and this is 1 minus x, sorry what I'm saying, this is this is basically minus 2 choose n, which is here we are referring to this minus 2 choose n xn. And now you just need to using this formula and this using this formula, so your here the closed form expression will be minus, since you have x square already. So if you want to find the coefficient of xn, this if you take this x square inside, the power series become minus 2n choose n x n plus 2. Now if you want to find the coefficient of xn, it will be minus 2 choose n minus 2, and this is basically that expression. So is this fine? Did you understand?
Yeah, I need to revise it again.
Yeah.
I'll put that.
So if you assume this general binomial coefficient for now, then is this question clear?
Yeah, understood. I will do.
So like see, this is also like, if you like, here also we did some computation, but this is also one of the ways to compute this number.
Yeah.
Okay. So I have selected few questions from zeta function and mobius function, and there is some question from recurrence relation also. Which one do you want to discuss? Like
Mobius, you do it.
Huh?
Mobius.
Mobius. Okay, fine.
Mobius function is hash diagram.
Huh?
Mobius function with the hash diagrams are there, no?
Zeta function, you mean?
No, no, not zeta function. Hash diagram.
Uh, which diagram you saying?
Hash diagram is there, no? Hash diagram.
Hasse diagram. Okay, fine. Yeah. So yeah, so I have one question on this Mobius functions. So, okay. So this is the question. So we have P is a partial order set. Partial order set, we are talking about this partial order set where we are taking our set is the positive natural numbers and our relation is the partial order relation is that x is less than equal to y if and only if x divides y or x is a factor of y. So you are familiar with this poset?
Yeah, poset I have read.
Yeah, this one is also fine, right?
Yeah.
So this you can see is a partial order relation because this is so we are saying x is less than equal to y if and only if x divides y. So this is a partial order relation. For partial order relation, we want that it should be reflexive,
antisymmetric, and transitive.
And you see that like all these three conditions are satisfied because
that's clear. Yeah.
So this is our poset, and now we want to find Mobius we want to find some values in the Mobius functions. Your a is any natural number and this is p1a. Okay, p1a is any natural number and p1 is a prime number. So if you consider so n plus, this is a huge poset. So if we want to just consider this interval a p1a. Okay, so first of all, is there using this partial order, are they related? A and P1A, are they related in this partial order?
No, they are not related.
So basically, this one is A and this one is P1A. Your partial relation, they will be related. A will be less than equal to P1A if A1 divides P1A. Does A1 divides P1A? Sorry, A divides P1A.
8 will divide the P1A, it's correct.
Yeah, so they are related by partial order, right? Now if you want to consider the Hasse diagram for just Hasse diagram as in just this interval. So you have this, this is a big poset, but if you just want to consider this Hasse diagram for this interval, so we have that we get that A is less than equal to P1A, right? So P1A should come above A, right? In the Hasse diagram. But is this fine?
Yes.
So are there, can any other element come between A and P1A?
No.
Because A and P1, no other element can come between A and P1.
Transitivity should not be mentioned there.
Huh?
Transitivity should not be mentioned there in Hasse diagram.
Yeah. Moreover, A and P1A differ by just one factor. So if your number was A, if you want to draw this Hasse diagram, so if we have A, P1, P2A. So now the Hasse diagram for B part, what will it be? That
P1A to P1 P2A, it can come, or P2A to P1 P2A.
Very good. Yeah. So this diagram will be this. So now we want to so A is this Hasse diagram and B is this Hasse diagram. Okay. So now we want to find first the Mobius number for A and P1A. So first of all, what is Mobius number of x, y? This is 1 if this is 1 if x is equal this is 1 if x is equal to y, and minus sigma Mobius xy this is so this is minus sigma mu Z Y. Wait, I'm writing it wrong. So what was our Mobius number? Yeah.
1 minus 1 and 0 it would be. 1 minus 1 and 0.
Yeah.
These are the three possible.
That was just for chain.
Okay.
Wait. Yeah. So see, like if you want to, oh sorry. So yeah. So see, our Mobius function was inverse of zeta function. Sorry, was an inverse of zeta function, and in general we had this formula that Mobius of xy is this. Like when if we construct the inverse, that if x is equal to y and sum over mu x z, where x is less than equal to z is less than equal to y, if x is strictly less than y. This was the formula, right? Okay, so like if we assume this formula for now, we can derive this formula using this. Like if we compute the inverse of our zeta function explicitly. Now if we have this formula, then for a chain, that is for a chain of this type, you have 0, 1 till n. This is your n chain, right? With n plus 1 elements, this is your n chain. So for this chain, we see that our Mobius function turned out to be this, that if it is 1 if x is equal to y, minus 1 if y is the immediate successor, that is y is equal to x plus 1, and 0 for all other cases. But this was true only for chains. Okay. For a general poset, it wasn't true. Why? Because we can calculate this. How do we using this formula we calculate this? So for suppose you have this chain. You have this chain 0 till n. We are talking about this chain. Now for we do it inductively. For if x is equal to y, we see that 1 is this. Now if x is less than y, we do it inductively. First we look at the case at x plus 1. Mu of x plus 1, right? So if mu, according to this should come out to be mu of x plus 1. So what all z should be sum it over? We sum it over mu x yeah, just mu x, right? Because we want to consider all those z which are strictly less than x plus 1 but more than basically which are lying in this interval. We want to sum it over all those z, and there is just one such z which is x. So we see that mu x plus 1 is minus 1. Is this fine? Why this is minus 1? Hello? So I think you lost the connection. So mu, this is minus 1. But now if we want to do it for mu x plus 2 say, so basically we have to sum it over all z which are lying in the interval x, the second, it should be strictly less than x plus 2. So what are such numbers? It can be either x or x plus 1. So this is basically mu of x plus mu of x plus 1. So we are doing it inductively. Mu x is 1 and mu x plus 1 from previous step is minus 1. So we see that mu x plus 2 is 0. And similarly for mu x plus k, we can see this will turn out to be, so what are the elements here? Mu x plus k will be mu x plus mu x comma x minus 1 x plus 1 till mu comma x plus k minus 1. And by induction we do it, mu x we get it to be 1. So and mu x plus 1 was minus 1. Mu x plus 2 is 0. So if it was 3, we would stop at here, and we see for k equal to 3 also this is coming out to be 0. So we see that this will be plus 0 0 0, so which will be 0. So for chains we see our Mobius function turn out to be this. Now our A part was basically, you have to find the Mobius function of A pKa. So you see that this is a chain like this. This is a one chain, and it is counting the opposite. It is counting the one chain, and we want to find the Mobius number corresponding to this, basically mu 0 1, and which from our previous calculation is just minus 1. So we see that Mobius number for A is coming out to be minus 1. Now we want to compute Mobius number for A, and when we have two prime factors. So we see the Hasse diagram for this was coming out to be this, as Anuj pointed out. P2A. Now if we want to count this, so since this is not a chain, we can't apply our previous formula. We have to compute it using our Mobius, using a formula for Mobius function, and which was mu xy. And we see that this A and P1 P2, this is strictly greater than P1 P2A is strictly greater than A. So here mu xy. So we are looking for x less than y, and our formula says it is basically mu xz, where we are summing it over where z is this, or in other words we can say z is belonging to close bracket x open bracket y. So now if we want to find out this, so mu of A P1 P2A, so we have to sum it over xz, where z is in this bracket A P1 P2 A open, and from this diagram we see that we have this and this, which, so it will come out to be mu A P1A plus mu A P2A, and mu A1 P1A we have calculated in our first step. Oh sorry, this was A PA. So this was APA, it was a chain this, and it was coming out to be this. So I want to clarify. So we were computing the Hasse diagram. So this was a chain of one element when k was 0, k was 1. That is, we were calculating A part was PA. So we were getting that when it is a chain of two elements or one, then it was coming out to be minus 1. So from our A part, calculation in A part, we see that this is 1, minus 1, this is minus 1. So this is minus 1 plus minus 1, which is 2. And so I leave the C part for you, and I'll do the D part. D part says, so I'll correct what I did earlier. So A pKa. So now first of all we have this relation that x is less than equal to y if and only if x is a factor of y or x divides y. So now if we have A pKa, so pKa is not the immediate not the immediate upper bound. So what all numbers can come between? It can be PA, P square A till PK minus 1A. So we see that APKA, the interval APKA, this is the chain of K elements, chain of K plus 1 elements, and this is basically isomorphic to K chain, right? Because this is just isomorphic to K chain. It is a chain of K plus 1 elements. And now we know for chain we have already computed. So mu APKA, under this isomorphism, this will correspond to mu 0K. And since K, if K is greater than, so this will be 0 if K is greater than 1 and minus 1 if K equal to 1. So we see that mu of APKA is 0 if K, if K is equal to 1 and 0 if K is greater than 1 and minus 1 if K is equal to 1. So this was our computing Mobius function for some of the problems. So there have been decline in attendance from last few weeks. So if you are watching this on YouTube and not please, I'll request you to attend the live session if you are enrolled in the NPTEL combinatorics group. We can discuss any problems that you'll be interested. We can discuss any problem that you all will be interested in. Thank you. I'll stop recording.